Hi, good evening again, everyone. I'm Ignacio Jean, the Executive Director of the Caribbean Water and Sewage Association, and we welcome you to our regular webinar. If it's Wednesday, it's CAWASA's Wednesday webinar. And today we have a special guest who will present to us on the Airvac vacuum sewer systems. My first encounter with this such a presentation was during the IWA conference held in Kigali last December, where I had the opportunity to sit in a presentation by Mr. Zhang Volker of the group. And it was such a fascinating presentation that I thought I would follow up with him. And there he has his representative for the Americas region, who will be our presenter today. He's Mr. Jerry Gala. Is the Americas Global Regional Manager for Airvac vacuums, sewer systems, excuse me, where he is actively engaging new clients in regions with challenging topographies such as Alaska, Central, and South America. He has an expertise in vacuum systems covering aspects from installation to maintenance. His career history includes a role in the packaging industry, where he enhanced performance for notable clients like Hillshire Farms, and Sierra Lee. Additionally, he has experience in energy conservation, collaborating with both federal and public organizations. So this evening, he is going to present. His presentation addresses the increasing need for effective wastewater solutions in areas lacking public sewers, especially where traditional gravity sewer systems are impractical due to the challenging topography, high groundwater on stable soils. And I'm really impressed with the numbers that we have with us this evening. So I now hand over to Mr. Jerry Gala. Thank you, Jerry.
Thank you very much. I appreciate the introduction. I'm not really sure how many people are familiar at all with vacuum sewers. Let's see here. Anna, are you the one sharing this or am I?
Yes, I'm sharing. I'm Anna. I'm located in Brazil, and I work with Jerry and in Latin America. So we both are kind of flu, so we help each other. This weather is crazy, you know. So I'm sharing my screen. So let's continue.
Yes. Another. Okay, so today, what we're going to do today is we're going to go over the operation of vacuum sewers. We're going to look at the major components, which there's 3 of them. We're also going to look at some of the advancements in the technology over the recent years, and then also look at some of the applications that we have in the works globally. So vacuum is not new by any stretch. It's actually been around since the 1800s. The technology was brought to the US by Electrolux company, and we later, Airvac got the technology, and then Acceptance Group as a whole is the owner of Airvac. So it's been around a long time. We have systems that have been put in the US in the early 70s, which are actually still in operation today. Okay, go ahead. So as far as our systems globally, we have roughly 450 systems in North America, and then another 631 plus in Europe, Australia, Africa. This is just the systems, and that's so connection wise, yeah, we're hundreds of thousands of connections. Go ahead. I'm sorry. So we're looking at the three major components. We have the valve pit, the vacuum main, and the vacuum station. We'll look at these a little closer. Can you advance? So the way the system works is the vacuum pumps, they create a vacuum on the collection tank, and you have the vacuum mains that run out to, can you, one more time? The vacuum mains, they run out to the pit itself. So that's where your vacuum source is coming from. Click again. The gravity line from the dwelling goes into the pit. As that fills up, as the lower sump fills up, there's a sensor tube in there that's nothing but a chamber of air, and that chamber of air gets compressed. So as the sump level rises up, it compresses a chamber, it compresses the air, and it shifts a controller on top of the valve, which we'll look at a little bit later. So when that valve shifts, it applies the vacuum from the front of the valve and allows the valve to open. Thus, it lets the contents be evacuated. And then we follow that, and this is very important because we follow that with atmospheric air. So that atmospheric air is what's actually propelling that sewage. So as the valves open and close throughout the system, the vacuum will be depleted. When it starts to go down to a low set point at the station, at the collection tank, the vacuum pumps will kick on and get it back up to the high set point and then shut off, and then the process keeps going over and over again. So when we're looking at the valve pit itself is H20 traffic rated without a concrete collar. It has two chambers. So it has the lower chamber, which houses the incoming gravity line, and that's where your wastewater is going to flow to. And you have the upper chamber, which houses the valve and the outgoing vacuum line. So of note, between the top and bottom chambers, they are completely isolated from each other. So if you're an operator, you're not having to deal with raw sewage. If you're messing with the valve at all, that picture on my right, you can see the inside of the upper housing with the cover off. When we have higher water users, such as a school or a hospital or laundromat of some sort, we'll use what we call a buffer tank. The buffer tank can be either single or dual, and the buffer tank itself has all the same equipment, same components as the valve pit. However, it's just a larger capacity for that higher water user. So, as I mentioned earlier, when the sump begins to fill, you have a sensor pipe, that pipe that's represented with that blue arrow. All that is it's a simple column of air, and that column of air is being compressed, and there's just a line that goes up to the top, up to the controller there. And go ahead and click again. So as that pressure builds, it'll shift that valve, and it's simply a three-way valve. So it's allowing the vacuum on the front of the valve to shift that valve and apply vacuum to the valve itself, which will pull that piston up. It has a simple little turn setting on it, a little lever setting that allows you to adjust how much air comes in behind. So once that sump is emptied, it's going to empty on roughly 10 gallons of fluid. That'll take about 3 or 4 seconds for it to empty. We'll follow that up with anywhere between 5 and 10, 11 seconds of atmospheric air. And again, that's what's pushing and propelling that sewage towards the vacuum station. Okay. So with the valve, it's very simple. You've got the controller up at the top. That's what I call the brains of the operation there. You have the what we call the valve operator and the Y body. And this is all glass-filled polypropylene, which is chemical and corrosion resistant. The operator in that controller, the controller can be removed with a simple slip key, like in the next slide, but the valve itself just screws in and screws out. So it's a threaded Y body. So that Y body would stay in the pit. And if you had to remove the valve for any reason, you would simply either, you would have to take off 3 lines and then simply screw the valve out and then screw a new one back in. Here's a closer look at the controller itself. We call it an HP controller. This is the newest generation of the controllers. If you look to the right in that clear area, that's where the pressure diaphragm is. So when that air, that compressed air is coming up, it's pressing on that right-hand side, and it's simply shifting it from that area right there. And again, there's just a slip key for easy removal. When you're looking at, how do we put the pits in, how many houses can use a pit, things of that nature. Generally speaking, we're using one pit is servicing between 2 and 4 houses. The real controlling factor here is how far the houses are away from each other, because we have to accept the gravity line. So if the gravity line is too deep, then we would probably put another pit. So, but a lot of times, houses are close enough where we can gather at least 2, if not 4, gravity lines coming in. And we had mentioned about the atmospheric air. So the way we introduce that atmospheric air is with this air terminal. So that air terminal would be placed somewhere out of the way, somewhere within 30 to 40 feet. Is 30 to 40 feet is the maximum distance away. So, anywhere within that distance away from the pit. Again, you can have 2 to 4 houses on one pit, but you only need 1 air terminal for that. Okay. With the next gen, the monitoring, the evolution of vacuum sewer systems, we have our monitoring equipment. The monitoring simply has the radio. There's to the top right there, you see the valve with the Y body. There's a micro switch that's in there. So all the valves come with this micro switch standard. And the lower component there is what we call the breather. So we can either measure and monitor your valve opening, closing, your time of open. We can also monitor your sump levels. And then we can use that information to give you a lot of different warnings or help with proactiveness and maintenance and operation of the system. This is just a little more information on the monitoring. We are using LoRa, and it is real time. There's the opportunity for bidirectional communication with LoRa. And then we're also, when we collect the data, we're able to look at it and do modulation with our vacuum pumps. We're able to open and close. If you have smart, you're able to open and close to reduce the chances of waterlogging or to clear the lines if you know that you have a large user coming on. So there's a lot of a lot of proactive measures with the monitoring, not just being reactive. Okay. Yeah, so the monitoring, it is cloud-based. Again, it helps the troubleshooting, it helps be a much more of a proactive system. And then if you are running, you know, modulation of the pumps with smart, we're able to be proactive in opening and closing valves, placed strategically along through the field. A little bit more on smart. Simply, smart is when you have a vacuum system, what we're looking at, we want a nice vacuum from the collection tank all the way to the end of the line. The way that you lose vacuum is if you have what we call a waterlogged condition. So if you can imagine a plug of water being like a wall or a door, you're going to have vacuum up to that point, and you're not going to have much, if any, vacuum beyond that point. So the way we move the fluid is with the introduction of atmospheric air. So smart introduces that atmospheric air based on different conditions, whether it's a timed condition where we tell it when we want it to open at 7 a.m. to clear the line before a school opens, or if it is a looking at vacuum levels and it sees, you know, we have a set point of say 10 inches of mercury, and once it hits that, we want this valve to cycle, just to be proactive measure so it doesn't waterlog. So there's a lot of different applications that we can use smart with that help the system with its efficiencies. The vacuum mains, as you notice on the left, the vacuum depth we run what we call a sawtooth profile. We're generally keeping that at 3 to 5 feet below grade. Whereas gravity, we all know, you know, gravity can run deep, upwards of 25 feet. So we don't have to deal with the dewatering issues and everything of, say, a gravity system. Generally speaking, we use between 6 and 8 inch pipe is typical. 4-inch on the service laterals. We do recommend the SDR21 with the Reber type gasket, which Reber gasket is simply a vacuum certified gasket. Go ahead. Here's a little closer look at the Reber gasket. It's vacuum approved. It's a double lipped locked in gasket. I mentioned that sawtooth profile. We use this sawtooth profile to gain elevation and to keep the network, the pipe network at that 3 to 5 feet. So the goal is we don't want waterlogged, so we never want a full pipe. So we're running in that lower picture, you'll see 1/3 sewage and 2/3 air. So we want the vacuum running over top of the sewage, so that we're always having good vacuum to the end of the line. And we do this sawtooth. It's all being enabled by these simple things we call lifts, which are just 245s with a PVC in between. So a little bit more into the vacuum mains. When we're on level ground, we're just using that 0.2% slope. So after 1,000 feet, we're going to drop a foot. So we're going to just use that 1 foot lift to get back up to our starting elevation, and then just do that over and over. When we're going uphill, we're going to use those same lifts. We're just going to space them closer together to gain that elevation. And then of course, downhill, we just follow the slope of the ground. Just a little more in the mains. We never use T's in vacuum. We always want a nice smooth 45. And then we also, when you're doing the service laterals, that 45 is clocked at a 10 or 2 position on top. troubleshooting purposes, for maintenance purposes, we do use isolation valves. And they're just resilient wedge gate. We'll have these at certain intervals along the main line, and then at all the branch lines, we'll have those at the branch lines as well. So if you need to service the system, you don't have to shut the whole system down. You can just isolate the area you need. And just one little quick more thing about the pits. So when you set a pit, it does come with a flexible connector, so it gives it a little more flexibility with the setting of it, and you don't have to use a lot of couplings. Yeah, so if the fixed point, another fixed point, and then the flexible in the center there. We mentioned about what we really care about is what the end of line vacuum is. We can measure the tank. That's great. If we're not getting vacuum out into the field, then that's where we need it. So this is how we're doing that. We have it works with our monitoring. It's just simply end of line. It's just communicating back with low raw what the end of line is, and then if we're running modulation or any sort of the next gen products, then it all incorporates together. The vacuum stations, generally speaking, are 2 stories. I believe it's the next slide or the one after. It'll show you some different configurations. Yeah. So all your vacuum stations are going to have your sewage pumps and collection tank. And if you look at the PackVac 2 right there, the sewage pumps and the collection tanks are in the basement. The vacuum pumps and control panel are upstairs. The reason why we generally put the collection tank in the lower side of the building is because we don't want to waste all of our lift. If we're 4 or 5 feet below ground, we don't want to lift all the way to grade and then have to go another 4 or 5 feet into the tank. So there's with vacuum, there's only a certain amount of lift that you can do over the course of a main run. So we want to limit how much lift we use to get it into the tank. So that's why that's the more common configuration. Prefab buildings, we offer prefab buildings. Go ahead. That's, yeah. So here's some examples of some vacuum stations. They can be designed in any way desired. A lot of these, like the top left one, that's in Oak Island, North Carolina. It looks just like the houses next to it. The Broad Creek down there in South Carolina, that is a prefab that was basically set in place. Everything that all the skids. So what we refer to a skid is the vacuum skid, where the vacuum pumps are, the sewage pump skid, collection tank. Prior to any delivery, these are all tested at the factory to make sure that everything is working correctly. Okay. And if you recall, there's no power out in the field. So any power that's needed is all at this vacuum station. So we do suggest standby generators. So in case there's a power interruption, the generator will kick on and your system will work without any issue. Occasionally we'll need odor control if it's in a area that is populated greatly. So with that, the simplest way is to just use a filter media bed So that's just simply wood chips. Carbon filters can be used. Different types of odor control can be used, but the biofilter is probably the easiest and least expensive method, other than just piping it directly to atmosphere. So again, when you're looking at vacuum and gravity and other technologies, vacuum, it's much more shallow trench and narrow trenches, so that's less excavation. With more shallow, does the system require a mixer? No. With the grease, the question was just asked about the grease. The grease does, so when it's being evacuated from the pit, it's at 15 to 18 feet per second. So it's a scouring rate. So nothing really sticks to the walls. Anytime that you get the wastewater to the collection tank, from the collection tank past, you may need, you may need to put something there if there is issues with a large collection of grease or things of that nature. But from the pit to the collection tank, we generally don't run anything regarding grease mixers or anything like that. I hope that answered that question. With the yeah, so less surface disruption, less restoration. If you do have existing utilities in the ground, we are very flexible horizontally and vertically with that by using those lifts, and or just using 45s to navigate around, and then a 45, to get back in line. Here's a couple pictures showing some routing around of some current piping. With the gravity, as we all know, gravity, it's basically, runs down, you pump it up, run down, pump up. Well, you need power at each of those lift stations and maintenance at each of those lift stations. In the ideal terrain, the flatter the better. For us, we can eliminate up to 7 lift stations with 1 vacuum station. And then also, as a big note, we are a closed and confined, or not confined space, but we are a closed system. So once the water gets into our system, we have little to no I&I. So you don't have to treat water that unnecessarily. Okay. It is operator friendly, as we saw in the picture earlier. There's no contaminate, that you have that lower surface there that contains the wastewater away from the upper chamber. Okay. And most importantly, where does it apply? New or existing developments, communities. We do a lot of septic to sewer, where we're having leaching of septic tanks, sandy conditions, unstable soils. Basically, we say that the harder it is, the better chance vacuum is as a good solution. Okay, I'd missed that question, but yeah, if you want to go one more, I think that goes into some of our applications. So this is in Judeide, Brazil. It's on the right there is a vacuum station. The left shows the candy cane, which is basically the same as the air terminal. That's your air inlet. And then underneath that bush right there, you see the valve pit. And that's a sidewalk in front of a extremely beautiful home too. Okay. We are at Palm Island. It's one vacuum station, 1,200 pits on that one station. That's in Dubai. Chetumal. This is in a more of a urbanized, more of a store area than residential, but it is 2 vacuum stations, roughly 160 pits. Then still in Quintana Roo, we have this system, which again is in more of a commercial area. As you can see to the right, that's the depth of the trench. So no dewatering needed. So roughly, yeah, I think that's around 90 valve pits. In Tortel, Chile. This one is fair. When was this one put in, Anna? This was like just a couple of years ago, a year ago?
Yeah, this was made like during the COVID time. This is community far away from everything. So the only way to collect sewage there was a special project. So the pipes are under the path that they have there. So the reason why they use PAD, the black pipes, which is more resistant from the weather that they have, like from the warm, very hot, and to the very cold, is in Patagonia area. So yeah, they will extend this soon. And this is in Paraguay. This is the first vacuum station that they installed there. This is a new development area, and they collect commercial buildings, 2 commercial buildings, restaurants, and an island with a marine, with homes, lots, and they are going to extend soon as well. And this is the last one made in Mexico, was to the airport, Tulum Airport, International Tulum Airport, just finished this construction in February.
Yeah.
We are in, can you continue?
No, yeah, you can go ahead.
Okay, so I'm sorry about my English. I'm Portuguese speaker, but if you cannot understand, just ask. We are helping in different countries to include the standards for collecting sewage with vacuum systems like an alternative, because we understand that we can help engineering to make better work in flat areas, in areas when you have difficulties to excavate, and that's why we call ourselves to like an alternative solution. We are very close to our customers always, because we start with the specification, with the project, helping to make the project as well, until the operators. So we provide continuing trainings for the operators, and we have the portal which make us close to our customers. So we have like trainings, videos in different languages, and we have as well all the projects that can help you to understand how to build your own project. So it's a way that we have to be close. So we are open to questions.
Yes, I think there was one question about,
Yeah,
In the chat, we had a question. I'll get it for you. There were two questions. I think you answered the first, which was, does the system require a mixer? How
right,
do you manage grease?
right. I
And
think I did answer that. If I didn't answer
yeah,
it well enough, I can.
and the second question is, with the absence of manholes, how do you deal with chokes, blockages?
So with that, we do have the manhole cover, right, where you can pull out and you can access the lower sump. There's three penetrations in that deck between the upper and lower sump. So you can access the lower sump from the upper. We just have it in grommets so that we can reduce I&I as much as possible. And then once it gets into the system, it's moving at 15 to 18 feet per second, which is considered a scouring velocity. So we've never had issues with anything getting clogged in the mains, because the mains are the bigger pipes. So yeah, if it can get into the pit, it can get through the system to the collection tank.
yeah. The gravity line from the homes arrives at the lower part of the sump, and everything was sucked from a pipe here, and the valve has 3 inches, which is kind of the same or a little bit bigger than the toilet.
Yeah.
So everything will be collected, and the velocity around 5 meters per second. It's very high, so everything will arrive at the tank kind of liquid.
And Derwin, I think
Okay,
Derwin.
Darwin, go ahead,
Yeah.
yes.
Hi, afternoon. Thanks for the, are you hearing me?
Yes.
Yes.
Hi, yes, thanks for the presentation. A couple of questions. Where the actuation valve for the vacuum that creates the vacuum for the first collection pit coming from the houses and from the source. The gentleman said that there are sensors and stuff to indicate certain parameters. Is there one for leaks, or how is it detected? I know you said you have like a compartmentalized pit.
Right.
One
So
is it. Go ahead.
Oh, I'm sorry. So if there's a leak, excuse me, I'm sorry, my throat's. If there's a leak in the system, you'll notice the pump run times will go up. So if a valve hangs open, let's say, and you have monitoring, you'll get a notification that the valve's open. Okay, if it's open past a certain time, in seconds. There's also another more economical way to determine whether a valve is stuck open or not, and it's simply with a solar light, which mounts to the air terminal. That's the second method. And then if there's an issue with a vacuum main or service lateral or something of that nature, you're going to start to see your pump run times creep up on your vacuum pumps. And then it would simply be, you can shut off, let's say you have two vacuum mains coming in. You can shut off the isolation valve to the 2 mains and see which one holds vacuum and which doesn't. And that's going to tell you which line your issue is with. But once the vacuum mains get put in, unless somebody's installing utilities or something and runs a drill through it, you generally never really have any issues with with the vacuum mains. That's why we use 45s too, not 90s for fittings.
Okay. The second question is, hello?
Yes.
Hi. Yeah, that was good. The second question is for the valve itself for the Y body. You said it's chemically the coating on it. It's chemical resistance to corrosion, etc. Do you all take into consideration like the hydrogen sulfide environment to be in? Because just from experience, these stuff would have been coated. I don't know if there's a different type of material from 10 or 20 years ago to now. And this stuff, the parts, it doesn't last. It's not as durable as it was. So that's another question as far as
Yep.
would it stand up to that test of time? Also, too, what is the change? What is the turnaround times on these parts and the system? So how long does it last generally?
Okay. A great question, and it's actually the material it's made out of. So there's no coating on it. It's the actual material, and it is. We have some of these valves. The ones from 1970 that we had put in are still the same valves being used today in that system. So these valves, it's nothing to get 20, 30 years out of these valves. Rebuild time is around 15 years. With the rebuild, it's simply some rubber components inside. So yeah, the longevity of them is very, very high. And we don't have any issue with the H2S gases or anything, because it's actually the valve itself is not in the H2S gases. It's being sucked out at 10 gallons. So very seldom you ever have fluid in there for long enough to get septic. But yeah, the valves, we don't have issue with the material at all. And it is not a coated material. It is the material itself. And then, I'm sorry, we have valves in stock. We have rebuild kits in stock. For something like that, the cost is not extremely high. If somewhere between the $40-50 range for rebuild, and when we do put systems in, we have a suggested spare parts list, which is not very extensive, but it handles the main items.
Okay, great. Thanks. Good information.
Yes.
Appreciate it.
Yes, sir. Thank you.
Yeah, the floor is open. Because the system, you've shown how you do the collection, but at the end of the system, what happens is that you have a treatment system for the
So
effluents that you have collected?
we handle the collection side. So once it leaves our four walls, we can either pump it to a lagoon or to a wet well or a treatment facility that's already, force main it. But we do not handle outside those four walls when it comes to after the collection side.
Okay.
So
it's just strictly a collection system, but you don't deal with the treatment system.
Right, it would be a collection system, yes, not treatment.
So, for example, if a utility were to go in that direction, would it mean that they'd have to establish now a treatment system at the end of the line, or would it be a larger sort of collection system where they can maybe truck it out to a main treatment facility? Is that what you were suggesting?
Yeah, but I mean, it's not uncommon to pump, there's we have some clients that will pump into a wet well and then they'll force main it miles away. We can size our sewage pumps to, it depends on the terrain, but, we can size our sewage pumps accordingly to pipe it to wherever need be. There's others that use lagoons. So I guess it really just depends on the municipality or the town or the application itself. But yeah, as far as the actual treatment, we're flexible. But all we can do is pump it to where it needs to be.
Okay.
Yeah.
Also, it seems to be, well, what are some of the advantages of such a system? I think you, in your opening slides, was that the suitability for areas where you do not have um, lots of water availability, or you have a bit of water scarcity
Yeah.
and
So
terrain issues.
yeah, so terrain issues, it's towards the end probably. The terrain issues is a big one. So since we are only going, 3 to 5 feet, dewatering it's not as great of an issue as, say, gravity. Also, if you're doing this in existing communities, if this is like a septic to sewer conversion or something of that nature, we're using a lot smaller equipment, where our trench is tiny compared to, say, gravity. So smaller equipment, dewatering is minimized. We're also using, on average, 1 to 2 size smaller piping than gravity as well. And then we do not require, since it is a scouring velocity, we don't require any flushing or jetting of the network either.
We have another question in the chat that is for a treatment plant already, or for a treatment plant already designed for a particular flow, how does this system affect daily flow compared to a gravity system?
Let me see.
From a treatment plant, existing treatment plant, we have to consider the vacuum station according with this flow, and we will collect this flow. But the way that we used to work is according with the area, we can specify the vacuum station. That is the only place that we need power energy, and then from this place send it to treatment plant. Sometimes we can make the vacuum station very close to the treatment plant, but sometimes according with the topography and the flow that we have to collect. So each project is a special solution. So we can analyze it if you want, or any project that you have, we can analyze it and make a layout and an estimate for free without charges. And then maybe you can understand better the area that you already know, for example.
Yeah, and with the flow though, our flow is whatever our flow is, we have very little INI, so you're actually going to get more accurate flow than you would, say, from gravity, because during a storm, you're going to be treating a lot of water that is doesn't need to be treated. So with how it would affect daily flow compared to gravity, it would be less than what gravity flow would be, because of the non-introduction of the INI.
Okay, I don't see any other questions in the chat. Are there any other questions you have? Any comments? See someone just log in. Yeah, well, I thought that was excellent presentation, introducing us to yet another system of collection and managing waste. I think you mentioned I think you started with the description of the system, the cloud-based, the smart system, and right through to the end of the line. I think we're very appreciative. And if there are no other questions, I'd like to thank you, Jerry and Anna.
Thank you.
For sharing your time and experience with us. And we, of course, this is being recorded, and which we will share with all the participants and some of those who may have registered and couldn't make it this evening, so they would have the opportunity to view it. And they can always reach out to you.
Thank you very much. I appreciate the time and allowing us to introduce our wonderful technology, and hopefully we can work together sometime in the future. And I do apologize about my throat. I've gotten a little bit hoarse. I think I've got a little cold or something. So I apologize if
That's
it's a
fine.
little hard to understand.
Yeah, hardworking people.
Oh, goodness.
Yeah, thank you very much. This is I'm Ignatius Jean, Executive Director at CAWASA, Caribbean Water and Sewage Association. And if it's on a Wednesday, we discuss everything from A to Z in water and wastewater, and introducing our water operators to emerging technologies and issues in this very important industry. So thank you very much all, and we're signing off. Good evening to you.
Thank you.
Thank you for joining. Bye-bye.
Bye.
Bye, gracias.